Hello and welcome to another power electronics class. In the previous class, we finished AC to DC converters. Other words, they're called rectifiers as well. The harmonics that we have in AC/DC and ripple factor and how we measure the ripple factor, the ripple current and the ripple voltage. Today, we will start with another important converter, which is a DC to AC inverters, what we call inverters. And specifically, we will talk about the DC to AC pulse width modulation inverters or PWM inverters. Now, what is an DC to AC inverter? So an inverter, and most of the time we just call it an inverter. We don't call it a DC to AC. We call the DC to DCs converters and DC to AC or AC to AC converters. We call the AC to DC rectifiers, and we call the DC to AC inverters. So when you hear the term inverter, it's most definitely the DC to AC inverters. And you see a lot of that in different appliances. For an example, you see you have an inverter HVAC system or a refrigerator that works with an inverter. And I would explain why we would use that. So an inverter or a DC to AC inverter converts AC to DC. Converts DC to AC, and the DC is the input, the AC is the output, and we have different type of inverters, but the one that we are mostly interested in is the sinusoid AC inverter. We also have square inverters and so on. For the inverter, we can have variable frequency and amplitude, meaning we can change the output frequency and control the output frequency for the AC signal, or we could control the output voltage as well. This is the block diagram or graph that we show for an inverter. So you can see the DC input, and we're going to have an AC output. Again, the output could also be like this. Could also be a pulsating, square signal as well. So we can have a square signal, we can have a sinusoid signal, we can have a triangle signal, and so on. And I'll explain which one of these we use for what applications. So some applications of inverters are adjustable speed AC drive, induction heating, standby aircraft power supplies, UPS, which is a big market for these. The UPSs are the uninterruptible power supplies for computers, and the HVDC or high voltage DC transmission lines. Other applications that I see for inverters are for HVAC systems, and they have become very popular in recent years. And the reason is that previously in the older generation, they used to utilize AC motors for HVAC, and the problem with AC compressors, and as you know, the HVAC works by compressing a gas into a liquid and then releasing the pressure at the condenser, and we have a condenser that we condense the gas, and it generates a lot of heat. That's the reason you see in the outside unit has these radiators, and they are for cooling the gas and compressing it. And it becomes a liquid. It's pumped in to the inside unit, and then the pressure is released. It absorbs the heat to evaporate for the liquid, and then it becomes a gas and then goes back to the compressor. So previously, the compressor was an AC system, and the problem with an AC motor, a pure AC, was that in an AC motor, you can just turn on and off the system, okay? You don't have any control of the speed. You can't put it like on 50%. It's either 0% or 100%. So it's turned on or off, okay? And that creates a lot of waste. Imagine you want to use 50% of your HVAC. You don't just want to turn it on and off. By the way, turning on and off the system is going to shorten its lifespan. It's going to put a lot of stress on the motor and the mechanical components as well. So to have a smoother start or turn off, or sometimes you need your HVAC just to work at 50% or 30%, they came up with DC motors. The problem with DC is controlling DC is somewhat, I've seen HVACs with DCs as well. Requires a lot of electronics, and the more important thing is DC motors, usually they have the brushes and commutators, especially the brush DC motors. I don't know if you're familiar with DC, and they require maintenance. You have to change the brushes, and it's expensive, and you have to do it, service them every 4 or 5 years. The next generation DC motors are the BLDC, brushless DC. Technically, it's an AC motor. And when they came out, the BLDC motors, they require control over the frequency and the voltage. And the next leap into this HVAC system was the invention, and actually inverters were around for a long time, but the semiconductors that made these inverters cheap and efficient made these inverters accessible, and this opened a new door for these HVAC systems, the new systems to be implemented. So now what they are doing is they are first using a rectifier to convert the AC to DC, which is pretty easy, just it's a bridge rectifier and a filter. And then we convert that back using an inverter to AC. Now you may ask, what is the benefit of going through all this trouble? When you have an inverter at the output, you can precisely control the frequency. And for an synchronous motor, asynchronous motor, or synchronous motor, like a squirrel cage, for example, AC motor, by controlling the frequency, you can control the speed of the rotation. Okay. So now what you can do is you can alter the frequency so the motor spins at 50%, 70%, or 100%. So you can have precise control on the AC motor. So you can go from 0 to 100% for the rotational speed. Now, another application for this is in EVs. The first generation EVs, like the Tesla Roadster, that used a DC motor, for example. Some of them, those early adopted, they use a DC, and they realized quickly that DC, you have a lot of loss. DC motors are more expensive. AC motors is much cheaper, actually. And they switch actually to permanent magnet, a type of AC motors that use permanent magnet. But the problem was controlling the speed, and therefore the inverters came into picture there. Now, I would say a vast majority of EVs nowadays use AC motors. Why? Because they are cheaper, very efficient, and they last longer as well. DC has a lot of benefits as well, and most of them are using a combination. It's a type of, I could say, BLDC motors. And for those, you need an inverter to be able to precisely control the voltage and the output frequency to have a smooth acceleration and to be able to precisely control the speed. So EVs as well. EV and HVAC systems are a huge market right now for inverters. Now, the inverters itself, they could produce different type of signals. Some of them produce a square wave signal. These inverters are the cheap ones that you see on Amazon, were 40, 50 bucks, like 1,000 watts. They're 1,000 watts nominal. In real world, they are much less than that. But these inverters can be only used if you want to run an electronic device. So imagine you want to run your laptop in a camper or an RV. This is good for that. Or if you want to run a heater. But if you want to run anything that has a compressor and a motor, this may initially work. Sometimes some devices have smart meters and smart systems to detect if the input signal is not good, and it's just going to produce a fault signal. It's not going to even turn on. But the older ACs, they turn on, but you would see a knocking sound, okay? And sometimes you even see the spark. Why? Because when you have a square signal, you suddenly go from positive voltage to a negative voltage. So you're changing the polarity immediately, and that damages the AC compressor. And again, it may work for a week or two, but it's going to get very hot very quick, and most likely you're going to damage it. But when you have a AC signal, the AC signal is going to gradually decrease and increase. So it's not going to suddenly go from positive to negative. It's going to go through very slowly to zero. It's actually not that slow, but in the motor's perspective, it's going to be slow, and then come back to negative and then zero and come back to positive. Yeah, go back to positive. So AC signal is, if you have a sinusoid, it's going to be smooth. It's going to be gentle on the motor. So anything that has a motor, you need a pure sine wave inverter. And you can see that if you go to Amazon, for example, you would see that it says, and it's good actually to search and see one of these. I would actually recommend that we look at one of these. Okay, let's search some inverters. And you can see that some of them, if it doesn't say pure sine wave, most likely they are like triangle, but some of them are specifically mentioning that it's a pure sine wave. And you can see here it's a pure sine wave. And the pure sine wave, you can see that the price is usually much higher compared to a normal inverter. So this inverter, it's a 750 watts, $53. This one, $214. And you can see that this is a normal inverter. It doesn't mention if it's a pure sine wave, and it's not, and it's around 22 volt. So pure sine waves are extremely expensive compared to a normal. So when you're going to buy them, make sure they are pure sine wave. And most of them that I actually tested, and I tested a lot of these because I used to work on solar systems, they claim it's a pure sine wave, but if you can connect an oscilloscope to it, you would see it's not a pure sine wave. It's close to it sometimes it's not even close to it. And another example that they use these pure sine waves is for PV systems as well, solar panel and solar systems as well. And those are the ones that are most expensive. You can see They can be $1,000, $2,000. This is for a 10 kilowatts. And SunPower, by the way, is one of the best brands. Caco, SACO, that's a German brand. SunPowers, all of them are the best brands that are out there. And these pure sine wave inverters can easily run a dishwasher, dryer, washer, and your HVAC system without damaging them. And they have a lot of protection system in them. So if the voltage drops or you have a surge in the load, it's going to disconnect to prevent damage to the inverter itself or your load. And that's the reason they're expensive. Most of them are capable of two-way power delivery, meaning some of them are also, you have the inverter that does the control system to be connected to grid. So some of them are off-grid and some of them are grid-tied inverters. When you want to buy them, if you want to build a solar system for a cabin, which you don't have any control connection to a transmission line, you're going to go for the off-grid one. It's cheaper. But if you want to have a solar system at your house in Amarillo and be able to sell the excess energy that you produce during the day back to the grid, you need a grid-tied inverter, which are more expensive than the other ones. Now, usually they have two inputs for a DC, and depending on if you have a single phase, three phase, they're going to have one phase output or two wires or 4 wires for 3 phase, depending on what applications that you are using them. And the other thing about these inverters, as mentioned, you can have a square wave, sine wave. There are also other types of inverters. Some of them produce a triangle. This is in between. It's not as good as the sine wave, but it's cheaper and it works well in most cases. And it's the signal that it produces. Obviously, it's better than the square AC. By the way, all of these are considered AC in term because it's alternative current, but it's not a pure sine wave. So when you want to buy an inverter, make sure it's a pure sine wave. If not, if it's okay when you want to connect again electronic, because if you connect your laptop, for example, to this inverter, the laptop again wants to convert the AC to DC, so it goes through a rectifier. So it doesn't matter. Actually, the square signal is better for it because you're going to have less ripples in the output. But if you want to run a motor and anything that runs on AC, this may cause a problem. So inverters are classified into two types. Generally, we have the voltage source inverters and current source inverters. A voltage source inverter, or VSI, is one in which the DC source has small or negligible impedance. In other words, a voltage source inverter has stiff DC voltage source at its input terminal. The voltage source inverters, one good example are the EVs, which you have a battery pack, large battery pack, and usually the input voltage is also constant. And the DC source, the batteries, have very negligible impedance as well. So EV is a good example of a voltage source inverter. And even some large like PV systems as well, solar systems as well. And we have current source inverters, or CSI. These are usually fed with adjustable current from an AC source of high impedance, i.e. from a stiff DC current source. And again, imagine that we have, before this, we have an AC to DC rectifier. And one example for this would be actually HVAC systems as well, could be an example of this. And in a CSI fit with stiff current source, output current waves are not affected by the load. Again, an HVAC system could be something like that. And this is these two show examples of a voltage source inverter. And you can see on a voltage source inverter, we usually have a capacitor, a DC link. The capacitor acts like a filter for a voltage and stores the voltage, so you can have a smooth, constant voltage in the input. And the current source inverter, you have an inductor series that acts like a storage for the current, and therefore you have a constant current in the input. So current source inverters are good when the load is changing all the time and you want to have a constant voltage. Now, the inverter switch control, the inverter output voltage can be shaped based on the switch on-off control that use with the inverter. Those two types of switch controls can be used, which are the square waves scheme, the schematics, and the PWM variable width scheme. Now, one thing that I want to mention is when we want to go from a DC to AC, we can do it using a switch by turning on and off the switch. Let me draw it with blue. So this is the switch is on, the switch is off. Okay. And we can create a square signal, and we can have 4 switches to actually have positive, negative. But here I just want to put it between 0 and positive. But if I add a resistor, for example, a voltage divider, I can make it multiple stage, meaning I can, instead of this, I can have something like this. Okay. And instead of having one switch here, I have 3 switches. So imagine if the output is connected like this, and I have 3 switches connected, for example, and this is my output. I'm going to call it switch 1, switch 2, and switch 3, and this is the source. So depending on which switch, I can open switch number 1, close switch number 2, and I can have this voltage here. So this is, for example, S2, S3, S1. So I can have like a step down, so I can prevent the voltage directly going from the maximum to the minimum. I can actually smooth it down a little bit. Still, this looks like a stair. It's not as smooth as a sine wave, but it's better than going suddenly from positive to negative. Because in low voltage, you're not going to have a big problem. But when it's high voltage, like 500 volts, 400 volts, imagine you have a switch connected to a 500 volt solar system, and it has 100 amps as well. Imagine how dangerous it is to switch it off and on. It's going to create sparks, and that sparks, those sparks are going to damage your switch. So the best way is to smoothly, slowly go through 0 and come back. And therefore, there are different ways. We can have the square wave, and we can also have what we call the PWM variable width as well. And we can, instead of having these resistors, we can have switches that have variable width, in other words, variable timing, so we can spread out that signal. So instead of connecting it at once, we can have like a sampling system that we can have multiple samples. The first sample would be 1 microsecond, second sample would be 2, third sample will be 4. So the higher the sample is, the bigger the sample is, you're going to have more voltage. And then you connect it to a capacitor and smooth it out. So technically what I can do is I can actually change these frequencies and the timing of these switches and have different samples, for examples, for them. Now, this is an example of a PWM variable width one. And as mentioned, you can use the resistor. Obviously, we don't want to use the resistor. It's a lot of waste, but I just wanted to show you how the concept works. And if you could control precisely control the timing of the switch, when to turn it on and off, you could have something that is relatively close to the sine wave. But what is the difference between the square one and the sine wave? This square one is easier and cheaper to build. You just need a op-amp to do it for the switching. But if you want to build a sine wave, perfect sine wave, you need a sophisticated control system and a very fast switch. Okay, the previous switch, you have to switch 50 to 60 hertz, something like that. Double that, it's going to be 120 hertz. This one, it's around 200 kilohertz, megahertz. So a much faster switch, which is much more expensive, and a very precise control system to be able to build this sine wave. And what this does is technically, when you have a small, the average voltage is here, then the average voltage is here, and then it's basically connecting these voltages together. Okay. So you're connecting the samples that we have. Let me draw it with a different color. So basically what you see in the output is a bunch of dots, and then you can use a capacitor filter to connect these dots together and create that perfect sine wave. Now, we also have single phase inverters, three-phase inverters, and we have full bridge inverters and half bridge inverters as well. So a single phase inverter is usually classified into two types. We have a half bridge and H bridge, or the full bridge inverters. As shown in this figure, on left you can see the half bridge inverter. Half bridge inverter has two switches and two capacitors connected to them. And the full bridge or H bridge inverter has four switches. Now, the full bridge looks. Can you tell me what does this look like, the full bridge? If I replace the switches with diodes, what would this look like? Perfect, a full wave or bridge rectifier. This is technically what we call a Whitson bridge. So you can see that replacing the switches with the diodes or thyristors, you create a rectifier, which is the opposite of the inverter. And replacing it with the switch, you create an inverter. So the half bridge inverter, this is also known as the inverter leg. This is the basic building blocks for a full bridge. It could be used in three-phase and higher order inverters. G here is the center point. Both capacitors have the same value, thus the DC link is equally split into two. The top and bottom switch has to be complementary. If the top switch is closed, the bottom switch must be off, and vice versa. Why? Because if I don't do that, I'm going to short circuit. If both of them are on, what happens? The battery would be short circuited. And it's going to, imagine if you have a 70 kilowatt hour battery or a solar system, like a 400 kilowatt being short circuited, it's going to create a disaster. So when one is on, the other one must be turned off, okay, to prevent this short circuit. And it's the same for the full bridge as well. In the full bridge, if I connect S1, and by the way, S1 and S2 are connected, then I would have positive, negative, and then I want to have S3 and S4 connected as well to create negative, positive. So first one creates the upper signal, the second one creates the lower signal, the negative signal. Now, what happens if S3 and S2 are connected at the same time? It's going to bypass the load, and you're going to have a short circuit, which is going to destroy the source. Okay? And also, if S1 and S4 are connected, again, it's going to short circuit our system and it's going to destroy it. So for a full bridge, when S1 is turned on, S4 must be turned off, and S3. And also when S2 is turned on, S3 must be turned off. So we have to have a safety mechanism for that. This is suitable for low power inverters, big capacitor size, and not economic for high power ratings. So the one that we mainly use are, again, this is a half bridge. Again, we need a very large capacitor to be able to store that, and it's not economical for high power. Now a single, and this is the half bridge, by the way, half bridge. And for a half bridge, as you can see, when S1 is turned on, S2 is turned off, and on the load, you're going to have the positive side. So this is S1 is turned on. And when S2 is turned on, the positive or the load is connected to the negative. So you can see here S2 is turned on and S1 is turned off. And this is technically our virtual ground here. It's going to be our ground in the system. They're going to create positive, negative. And one other thing is that you can see when S1 is on and S2 is off, the voltage is VDC over 2. So half of the source voltage. And when it's turned off, it's going to be negative VDC over 2. So a full bridge or single phase is built from 2 half bridge legs. The switching in the second leg is delayed by 180 degrees from the first leg. Same time closing would cause a short circuit from VDC to ground, or what we call a shoot through. To avoid a shoot through, when using real switches, there are a turn on off delays. A dead time or blanking time is implemented. Therefore, either S1, S2, or S3, S4 are turned on at the same time. As mentioned, we don't want S1 and S4 to turn on at the same time, or S1 and S2 and S3 and turn on at the same time. Now, usually we want to have a breaking time between them from going positive to negative. So in reality, it's going to turn everything off for like a few microseconds and then go back to negative. So in reality, the signal we're going to look somewhat like this. It's not going to directly go from positive to negative. You're going to have a short breaking time between them. So what is shoot through fault and dead time? Again, the reason that we put this small dead time is because we don't want all the switches to be turned on at the same time, because it's going to explode the system. It's going to destroy the system. In practical, a dead time as shown below is required to avoid a shoot through faults, the short circuit, which is the short circuit across the DC rail. Dead time creates low frequency envelope. Low frequency harmonics emerged. And this is the main source of distortion of high quality sine wave inverters. And this shows the example of a shoot through. And as I mentioned, for example, if S1 and S4 or S1 and S2 is connected at the same time, you're going to have a shoot through, which is going to cause problems and destroy the system. So to avoid that, we usually have a dead time. And in the dead time, all the switches are open, meaning there is no connection between the input and output. And the reason is to avoid the shoot through again. If they isn't a dead time, there will be a microsecond that both of them are connected, and you're going to have a shoot through or a short circuit at this point, and it's going to damage the system. Now, to illustrate the concept of AC waveform generation, we use the following figure. And where the inverter starts is shown below. So first we have the S1 and S2 switch closed. If S1 and S2 are closed, or if they are on, then we would have a positive VDC over here, because the positive of this output is connected to the positive of the source. So you're going to have positive. And when S3 and S4 are closed, let me draw it with a different color, then the negative of this is connected to the positive. Therefore, we're going to have the negative cycle here. So here S3 and S4 are on. So this graph is for the first one. This is for the second. And the dead time is when S1, S3 turn off and S2, S4 is also turned off. Now, what is V out? V out is equal to VRG minus VR prime G. This is the R prime point voltage, and this is the R voltage. And G is our virtual ground. So it's the voltage between this and the virtual ground, and R prime and the virtual ground. R prime and R. So V output is actually oscillating between VDC, maximum VDC, and negative VDC. And this is the illustration for it. So S1 and S2 are turned on, therefore S3, S4 is turned off. And you can see that the current is going from left to right, and you're going to have a positive VDC at T1, T2. And by the way, this is for T between T1 and T2. And for the second scenario, the current is going from right to left. Therefore, this positive is connected to this negative, and you're going to have a negative or inverted voltage. And this is for S3 and S4 on, and S1, S2 being off. And for this scenario, T is between T2 and T3. Now, these are without dead time, so we immediately went through to that. But obviously, we want to have dead time, and I'll explain later on for the control. This is for just studying the switch. Next, we have the square wave inverter with an RL load. With an inductive load, I is laid behind the voltage, although the voltage wave is still square. At steady circuit condition, current wave shape becomes repetitive. The current will grow up exponentially during the positive half cycle from negative IN up to IP through this system. And again, as you know, in DC, we won't have any problems with the inductor or capacitor. But when you're creating an AC system, and you add an inductor or a capacitor, you are affecting the power factor as well. You're affecting the, you're making it or leading or a lagging power factor, and you're changing Q. And as you know, the inductor creates a delay in the current. So the voltage changes. If we had a resistor, we would have no problem. But since almost all of the loads that we have here for an inverter is usually a AC motor, and the AC motor is created from a bunch of wires, which are the stators and the rotor. They have wires that act like an inductor, and that inductor causes a delay in the current. And you're going to have a lagging, for example, power factor. If you have capacitors, for example, you're going to have a leading or lagging power factor. And that's the reason we add the capacitor bank. If you had measurement instrumentation with me, you remember capacitive bank are used to compensate for the power factor, to be able to actually shift this current and synchronize it actually with the voltage. Now, let's see how it works. So this is a real world example of a inverter. The inverter, for the switch, we use a transistor. This here, it's using a BJT transistor, and we use a diode for the freewheeling to protect the transistor. Exact same thing that we had for the buck boost or buck boost converters. We use a diode over there. Here we use it over here as well as for the switch. And again, you can see that by changing and turning on the switches, the output voltage is changing immediately. But the problem is the load here has an inductor, and the inductor current actually takes some time to change, okay? And the current actually slowly rises and it grows exponentially. And when the voltage is negative, again, it drops. So if we didn't have an inductor, if we had a resistor, the current would do this. It will be the blue one if you have a resistive load, for example. Or if you just connected an oscilloscope to see the output. But when you add an inductor, then the inductor, for the current for the inductor to change, it takes time because the inductor should charge. Okay. And this is also showing IN, which again, it's the IN is changing from the positive going back to 0 and back to positive. So going from negative to positive, 0, negative to positive. This is IN, by the way. This is I out. So you can see the I out is not directly going from back to 0. And the reason for this is that our load is storing the current and it's slowly releasing it. But the source doesn't have that capability. Therefore, the current is just dropping back to its initial value. And if we have a resistor, you won't have this problem. If you have a capacitor, the current will not change like this, but the voltage would have an effect. We usually don't have capacitive loads. So yeah. Now I out for this system is going to be V or R 1 minus 2 over 1 plus E negative RT over 2L E negative RT over 2L. So the output voltage for a square wave inverter with R or RL load is as shown below. And you can see the output voltage doesn't have any distortion, but the output current does have distortion. And it's just going to be a pulsating square signal. The instantaneous load voltage can be expressed using the Fourier method of analysis. Therefore, VL would be equal to V0 plus V1 plus V2 plus V3 into infinite. And where Vn is Vn hat sine wave of n omega t plus phi n, and omega is equal to 2 pi over t or 2 pi f. By the way, this is omega. For a square wave of amplitude A, Vn is 0 if n is 0 to 4, 6, and Vn is 4a over p pi n when n is 1, 3, 5, and 7. So you can see for odd numbers, it's 4a over pi n, and for even numbers, it's going to be equal to 0. And this is very important here. It actually shows the fundamental components as well and the harmonics. So VL would be equal to 0 for even harmonics, and the even harmonics don't cause any problem again, and problem is caused by the odd harmonics, 1, 3rd, 5th, 7th, etc. And mainly we have problem with the 3rd, 5th, 1st, 3rd, 5th. These have the most effect. The rest of them would have minimal effect. The peak and RMS values of the fundamental component of the load voltage are equal to V. F is going to be equal to 4e over pi, and Vf is going to be equal to 2 square root of 2e over pi. The load RMS current is determined from IRMS is equal to square root of 1 over t, integral of t from 0 to t, I square dt. And the load power, assuming negligible loss, P is equal to 2 over t, the integral of t from 0 to t over 2, EI dt. In other words, it's EI average. Now for a variable voltage, variable frequency capability, that's going to be much more complicated. The output voltage frequency can be varied by the period of the square wave pulse. The output voltage amplitude can be varied by varying the magnitude of the DC input voltage. This is very useful. For example, variable speed induction motor drives use this technique. So we learned that we can convert DC to AC by simply using the switch. Now, changing the switching frequency and timing, you could change the frequency of the output. And by changing the input amplitude, you can change the output amplitude as well. So let's imagine a scenario that we have a battery. It's a 12-volt battery, car battery. And I want to convert this, let's say, to a 6 volts, or now let's say 24 volts AC signal. How can I do that? So I want to go from a 12 volt to a 24 volt AC signal. And I want the frequency to be 10 hertz. The 10 hertz part is very easy. You can put a switch that turns on and off 10 times per second. How can I change the output voltage using this? Did you have an idea, Tyler? Perfect, great, that's excellent. Yes, that's the exact answer. If you use a boost converter exactly after the battery, you can convert it to 24 volts, for example, and then run that 24 volts through a switch or a chopper, and then at the end, you're going to have this is, by the way, our V output, and this is going by 10 hertz. So at the end, you're going to have a voltage that is 24 volts, 10 hertz, and the input was just a 12 volt DC. Okay, that's a great question. That's a perfect question. So a boost converter only acts on a DC, doesn't work on AC. But the reason I'm saying that's a great question is that imagine if I want to do 12 volts to 1200 volts AC, okay? A boost converter is not going to work well. Another thing that we can do, so imagine I have a 12 volt and I want to do 1200 volts in the output and at, for example, 60 hertz, okay? This is normal, you're going to see this around. So what we can do, instead of having the boost, okay, I'm going to have a DC to AC converter, DC AC. Now what I have is, for example, if I have a pure sine wave, I'm going to have a 12 volt AC. So I have a 12 volt DC in the input, and I have a pure sine wave, I'll convert it to 12 volt AC. Now the easier way to do that is simply run this through a transformer. And the transformer is 1 to 100. And then I would have a 1200 volt AC in the output, okay? Transformer is cheaper, but you need more space for a transformer. So some of these, that's a great question. Thank you for bringing that up. Transformer can be used to boost an AC signal, okay? But transformer cannot be used to boost a DC signal. If you connect it to DC, it's not going to work, okay? So two ways. You can either put the buck or boost DC to DC converter before the AC to DC to AC, or you can put a transformer after the DC to AC converter. Okay. Does that make sense? Yes? Okay. Thank you for bringing up that question. Depends, again, on your design, okay? What you want to build. And you may see this in your senior design project. One thing that I'm currently actually working on, this is just for me as a hobby right now. I'm building actually at home a electric drift go-kart. I built one like a few years ago. I'm building another one. That one has a 10 kilowatt motor, and I have an inverter and everything, and I'm actually halfway through. I have to find time to finish it. And the other day, actually, I was thinking to boost and change the motor. It's a brushless DC. I was thinking to change it with an AC motor. And actually, I was thinking of how much voltage I want and everything. Because now I have a 48 volt. And I was looking through all of that. And actually, I was designing something exactly like this. I wanted to put a inverter, and after that, I could put a transformer. But the problem with that was that even if you put 1 volt in the input, the transformer is going to boost that, and you have to find the threshold on when the chopper and also the DC to AC works. But you're going to see a lot of these problems in real world and senior design, and you have to come up with a genius way to solve it. So the better option for me for that would actually using a BLDC with just a PWM controller. It's going to be much easier. And when you do that, you can use the throttle system would be more responsive. When you're drifting, you want something to be, the throttle to be very sensitive and responsive. If it has a delay and the throttle is connected directly to the motor, we don't have any gearbox, so it's just a chain system. You want to be very precise to be able to drift perfectly. I used to do racing a lot, build cars, professionally doing go-kart, and then, you know, modifying cars for drifting as well. And so it depends. It depends on what applications are you going to use. Sometimes you need something cheap, so you're going to go with the buck converter and just simply, sometimes you need something very sophisticated and accurate, as mentioned. For that, you need to have a sine wave, pure sine wave, and then use that. So voltage source inverters, or VSI, with variable DC link. The DC link voltage is varied by a DC to DC converter, as you mentioned, like a boost converter or controlled rectifier. Probably I won't recommend rectifier again because the rectifier, it's good for very small voltage and small applications, but the problem with the rectifier is you're going to lose like 30–40% of the power. And we generate a square wave output voltage, and the output voltage amplitude is varied as the DC link is varied. So if you have a variable DC buck boost, you can change the output as well. And sometimes we actually need that. Why? Because we have a variable load, and when the load is suddenly connected, like the HVAC is turning on, the voltage is dropping. And you want to have a control system to immediately increase the input voltage to compensate for that, you know? So sometimes you want to be able, or for example, if you have the input is a solar system, and at noon you're producing 200 volts, but in the afternoon you're producing 100 volts, you don't want the output AC voltage to drop to half in the afternoon. So what you're going to have, you're going to add another DC to DC link, which is a variable buck boost converter, and you can precisely control the PWM on that. And that's the reason these inverters, the solar inverters, are so expensive, because it's a very complicated control system. And you have a DC to DC link as well. So you would change the DC voltage, which in turn changes the DC input for the inverter and changes the output voltage. Okay. And the frequency of the output voltage is varied by changing the frequency of the square wave pulse. So you have two frequencies to control. The first frequency that you want to control, F1, is actually controlling the duty of the first one, and it's changing the voltage. The frequency that you're changing the second time is changing the switching frequency, and therefore it's changing the frequency of the system. So the DC to DC link, when you change the switching frequency, you're changing the voltage. The DC to AC system, when you're changing the frequency, you're changing the output frequency. Okay, I think it's enough for today. Next week we will continue with the, let me mark it up to here, with the VSI with fixed DC links, like when it's connected to a battery, and the harmonics and so on for that. Thank you so much, and I will see you next week.